In this video, we'll record solutions to section 3.4 in our book. Section 3.4 is the chain rule. Now, just a quick review of the chain rule. The chain rule says if you're taking the derivative of a composition of two functions, we have the derivative of f of g of x. The chain rule says that you're going to take the derivative of f evaluated at g of x times the derivative of g of x. Now, in more common vernacular, we're going to say we take the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So you'll hear me use those words, and I'll be identifying which functions are inside and which functions are outside as we move through the problems. So we'll start with question number 5. Question number 5 says y equals e to the absolute value of x. Now we have a derivative rule for the exponential. We have a rule that says the derivative of e to the x equals e to the x, but we do not have a power of x. We have a power of the root of x. Now, if we rewrite that, that's of course e to the x to the 1/2. So our outside function, if we want to think about it that way, is the exponential. Our inside function is x to the 1/2. Following the chain rule, then, we would take the derivative of the outside function. Our outside function is the exponential. The exponential says if you take the derivative of me, you just get me. That's what happens. So our outside function is the exponential. So when we take the derivative of that, we get whatever that function was in the first place. Maybe it would be easier if we change this variable to something like u. Well, let's not make it u, let's make it t. So if that way we're not confused with the x over here and the x over here. So the derivative of the exponential says if you're going to take the derivative of the exponential, you just write the exponential down. You don't pay attention to what the power is because the rule says the power is just going to be the variable. So here my variable is x to the 1/2. So I just copy that down. Now the chain rule then says we have to take the derivative of the function that's inside. Inside in our rule is t. The derivative of t is 1, hence the reason we never do another step. But here our function's inside value or inside function is x to the 1/2. So we have to take the derivative of x to the 1/2. The derivative of x to the 1/2 is 1/2 x. We subtract 1, we get minus 1/2. Now, if we're going to express this nicely, we would have, this is a positive exponent, so that's going to stay on top, ex to the 1/2. Here we have a denominator of 2, and here we have x to the minus 1/2, which falls to the denominator because of the negative exponent. And if we get rid of the fractional exponents, because the problem began without fractional exponents, we're left with e to the root x divided by 2 root x. And that's number 5. If we skip down now to something like number 11. Number 11 gives us a function in terms of z, and it says my function is 1 divided by z squared plus 1. Now, when you look at this problem, if you think, well, I'm just going to use the quotient rule, that's perfectly fine. There is nothing wrong with that. The quotient rule will get you the correct derivative. What your author, or the author in this case, is expecting is that perhaps you would have rewritten this as z squared plus 1 to the negative 1. So you could avoid the quotient rule, is what the author was expecting you to do here. Now, if we're going to take the derivative of that, we're going to take the derivative of the outside function. So if I just put my fingers over this, the outside function is something to the negative 1/2. If we're just taking the derivative, again, I'll use a t, of t to the negative 1. The rule says you bring down the negative 1 and you subtract 1. Well, in this case, our t is z squared plus 1. So we're going to bring that down. We're going to bring down the negative 1, just like it says here. And we're going to have this to the negative 2. Z squared plus 1. So we take the derivative of the outside function. We leave the inside function alone. So we have the derivative of the outside function evaluated at the inside function, i.e., we just leave the inside function alone. However, we're not finished. Now we have to take the derivative of the inside function. That means we're going to take the derivative of z squared plus 1. The derivative of z squared is 2z. The derivative of 1 is 0. And so this is what we have. And again, if we're going to clean that up, this has a negative exponent. Here's a minus sign. So that's going to be negative 2z. And our exponent, here being negative, is going to force this into the denominator. So we have z squared plus 1 squared. Okay, so that's number 11. Let's skip down a couple here. We'll skip down to something like number 18. 18 is e, well, it's y equals, pardon me, e, our exponential again, but it's not to just a power of x or a power of t, it's to the minus 2t. So that's a function. We're going to have to use the chain rule. That's a composition of two functions times cosine of 4t. And again, that's not cosine of t. We know the derivative of cosine of t is negative sine t. This is cosine 4t. It's cosine of a function. On top of that, we have a product here, right? This is a product. This is one function times another. So we're going to have to use our product rule, and we're going to consider this to be our f and this to be our g. If we go back to our format from the product rule, f times g. The derivative here then is going to be the derivative of e to the minus 2t. Now that's very similar to how we took the derivative of e to the x to the 1/2. E to the minus 2t is an exponential. It's f prime g, right? We're doing the product rule, but inside the product rule, we happen to have to use the chain rule. So we're doing the product rule. We're going to go f prime, the derivative of this. It's an exponential, so we get the exponential back. All right, the derivative of an exponential is the exponential. Now, once we're done with that, we do have to take the derivative of what's inside. So the derivative of minus 2t is negative 2. Now we multiply by g. Remember, this is f prime g, so we multiply by cosine of 4t. Plus, because we have to do the other half of the product rule, f prime g plus f, so we copy that down, e to the minus 2t. And now we multiply by the derivative of g. Now that the outside function is cosine. So we multiply by the derivative of cosine. So that's going to be negative sine. And we leave the inside function alone. Times the derivative of the inside function. The derivative of 4t is 4. Now when we do our algebra here, right, we have negative 2 e to the minus 2t, and we have cosine of 4t. Over here we have a negative 4, negative sign 4. We have negative 4 e to the minus 2t again, and we have sine 4t. Now, we have to clean this up. We have to factor out common factors. There's a negative sign in both of these. We'll pull that out. There's a 2 and a 4, so we can take out a 2. Here's e to the negative 2t. Here's e to the negative 2t, so we'll take that out. And then what do we have left? Well, here we took out negative. We took out the 2. We took out the e to the negative 2t. The only thing left is cosine of 4t. Here we took out the negative. We took out a factor of 2 from 4, so that's going to be plus, right? Because we took the negative out, so we're going to get plus 2. We took e to the negative 2t out, so that's gone. And we have sine 4t. Okay, so that's number 18. So clean the whiteboard up here. And we'll continue going down through some of these homework problems too. Now, the only way that you become proficient with the chain rule is to just keep doing chain rule problems. If when you get done with the homework assignment, you don't feel like you're solid with the chain rule, you don't think to yourself, okay, I've got this. There are plenty of problems in the book that were unassigned that you can use to practice. You know, you can use all the odds, find the answers in the back of the book. You can go on the internet, find plenty of videos, right? Plenty of videos about the chain rule. All right, let's pick it up now. That was number 18. We'll go ahead and do problem 19 because it's a very famous problem to be included in the chain rule section. There's going to be a substantial amount of algebra that we're going to have to employ to do this problem. And so we're just going to have to keep ourselves focused on what we're doing and handle one step at a time. Okay. Once again, we have a product here. We have a binomial to the 4th power times a binomial to the -3 power. And we can't expand this. I mean, we could expand it, but we're not going to. Nobody wants to figure out what 2x minus 5 to the 4th is, or 8x squared minus 5 to the 3rd for that matter. So we're going to use the chain rule and the product rule again to find the derivative. And again, if we're thinking about this in terms of the product rule, this is our f, this is our g. Now, please understand that f and that g are from back when we were learning the product rule. Now, the product rule said if we're taking the derivative of f times g, we're going to take f prime times g plus f times g prime, right? That was our product rule. This f and this g are not related to the pink f and the pink g we've got written right here to remind us of the chain rule. So hopefully that notation is not causing you any confusion. So how do we find the derivative with the product? We take the derivative of the first term. Now, the inside function doesn't matter. That's a power of 4. And if you're taking the derivative of a power of 4, you bring down the 4. Your new power is going to be 4 minus 1, 3. You copy the inside. Derivative of the outside function, leave the inside function alone. Now we're going to multiply by the derivative of the inside function. 2x minus 5, the derivative of that is 2. Now that was our f prime. Now we have to write down g. Plus, we copy down f. And we're going to take the derivative of g. Once again, we have somebody to a power. If you have a power, you bring the power down, and the new power is minus 1. We leave the inside function alone. Now we're going to go back because the chain rule says to take the derivative of what you found inside. 8x squared, the derivative of that is 16x. The derivative of -5 is 0. Now we're not going to expand this, we're going to factor, right? We're going to pull out common factors. So what do we have here? We have 4 times 2, that's 8. Here we have a 3 times 16. So we have a common factor of 8. So we're going to bring out an 8. Here's 2x minus 5 cubed. Here's 2x minus 5 to the 4th. So you take out the smaller power. So we take out 2x minus 5 cubed. Now we have to do the same factoring with our negative exponent. In algebra, we were taught to always remove the common factor with the smallest power. The smallest number between -3 and -4 is -4. I mean, on the number line, -4 is here, -3 is here. This is smaller. So we're going to pull that out. That's our rule from algebra. So we take out 8x squared minus 5 to the -4. Now, what's going to be left? All right, what's going to be left? Well, let's take a look, and I'll change colors to help us here. What's going to be left? Well, over here, we took out an 8. That's 4 times 2, so those are gone. We took out 2x minus 5 cubed. So 2x minus 5 cubed, that's gone. We factored out a -4. So that's minus 4. That's how we do exponents back in algebra. When you factor something out, you subtract it from the previous exponent. In this case, we're subtracting -4 because that's what we took out. -3 minus -4 is 1. So that leaves us 8x squared minus 5 to the first, right there. Plus. What do we get over here? Well, let's take a look and see what we get. Over here, we took out an 8. That turned that 16 into a 2, right? 16 divided by 8, 2. We have a negative sign there. We didn't take a negative out, so we have -3. That gives us -6. I'm going to go ahead and write that like this. We'll clean it up in a second. We took out a 2x minus 5 cubed. So we take away 3, right? That's how we factor. We subtract exponents. That leaves me at 2x minus 5 to the first. Here, we took out 8x squared minus 5 to the -4. 8x squared minus 5, -4, that's gone. We have not factored out this factor of x, so that is also left here. So this factoring of negative exponents, that's one of the things that pops up in the chain rule homework in a calculus book. And we want to make sure that we're comfortable with that. And if that means we have to go back and watch this problem 2 or 3 times or watch another video, we have to do that. Okay, we have to. We can't avoid this. I can't factor out negatives. Yes, you can. And we're going to quite often. So you need to get used to how to do that. Now, typically, you can tell you've done these types of problems correctly if there are common factors over in this portion. If we just look at the bracket portion, we're going to leave this. It's here, but I just don't want to take the time to write it. This is to the first power. So that's 8x squared minus 5. Here we have x times -6 times 2. That's -12x squared. See how we have like terms? Here we have -6 times -5. That's 30x. Now what's going on over here? Well, we have an 8. We have a 2x minus 5 cubed. We'll go ahead and write that here. And you can tell probably by the fact that I've not left any room that I'm going to go ahead and move this 8x squared minus 5 to the -4. I'm going to go ahead and move that to the denominator. Okay. Now the only thing left at this point is to collect like terms inside of here. So we have 8. We have 2x minus 5 cubed. Here we have -4x squared plus 30x minus 5 all divided by 8x squared minus 5 to the 4th. Okay. So problem 19, those are very typical chain rule kind of questions where we combine the chain rule with the product rule with negative exponents. All right, so we want to be proficient at that type of a problem. I don't know how much more of a hint I can give you there. Let's jump down and take a look at something like 25 because it has trig functions. Okay, so what are we doing in problem 25? 25 says we have y equals secant squared of x plus tangent squared Now, before we even get started here, maybe in the back of your mind, something is, telling you, hey, wait a minute, there's a relationship between secant squared and tangent squared. And if there isn't something in the back of your mind telling you that, well, then you need to review your trig identities a little bit. Because we have a trig identity that says cosine squared of theta plus sine squared of theta equals 1. And if we divide this by cosine squared, and this by cosine squared, and this by cosine squared, we get 1 plus tangent squared equals secant squared. So we could, before we began this problem, if we wanted to, we could replace this secant squared with 1 plus tangent squared. And if we did that, right, we'd have 1 plus tangent squared plus, our variable's x, plus tangent squared x. Or we would be beginning, now we haven't taken a derivative yet, but we would have 1 plus 2 of those. The other thing we have to remember is that back when we were in pre-calculus, we said, okay, we're going to write tangent theta squared. That's going to, if we're going to have to write the square or the cube of the trig function over and over and over throughout our mathematical career, it's going to be very inconvenient to always have to write these parentheses. So we said, we took the convention, we said, we're just going to put the squared right here. Right? So when I have tangent squared, it really means this. In other words, this is really, if we write it again, we have not taken a derivative yet. It really means this. So we have a function to a power. We need the chain rule. So now we can take the derivative. The derivative of 1 is 0. This is somebody, something, some function squared. So we have a 2 here, right? Because that's a constant. When you have a square, you bring the 2 down. So that's going to give us another factor of 2. And then you have tangent x. You take away 1 there, and you're going to have tangent x to the first power. Now the chain rule says we've got to take the derivative of what's inside. The derivative of tangent is secant squared. And now we have 4, right? 2 times 2. Tangent x, secant squared x as our answer. Okay. So sometimes it's better to do a little algebra before you take the derivative. Now, if you would have taken the derivative straight off of this version of the problem, you would have eventually got to this answer, but it would have taken some trig substitutions. So that's 25. What about a problem like 31? Okay. 31, we have y equals 2, and now our power is sine of pi x. Okay. Now we have a rule that says if we're taking the derivative of a number like 2 or 7 or 12, a to the x, we get a to the x times the natural log of a. Okay. That's our general exponential rule. And I don't know if we've made a big deal out of that in class yet or not, but we needed to do problem 31, so I'm going to write it over here. Now that means we have 2 to a power, all right? 2 to a power. Now our power happens to be another function, but the rule doesn't care about that, right? The derivative rule doesn't care. It says, all right, if you have 2 to a power, you just copy down whatever you have. So we copy that down. Right, that's what it says, a to the x. You then multiply that by the natural log of your base, natural log of a. Okay, there it is. In our case, a is 2, natural log of 2. But it turns out our power is a function. So we have to use the chain rule. Right? We have to continue the derivative, we've got to take the derivative of what's inside. Now, what's inside is sine of pi x, right? So we got to take the derivative of sine of pi x. The derivative of sine is cosine of pi x. But we have to be careful here. Inside the sine is another function. That's not an x, that's a pi x. That's like 2x, 3x, pi x. So we then have to take the derivative of what's inside again. We have a function inside a function inside another function. We have 3 levels on this problem. So we've got to take the derivative of pi times x. Now, if you have 7x, the derivative is 7. If you have 12x, the derivative is 12. If you have pi x, the derivative is pi. So now there's no real nice way to write this. We can't put any of these things together. So, we typically put our coefficients out in front. This is our coefficient, so we put pi there. And from there, it just becomes what order do you want to write them, right? So I would write them as pi. There's no right or wrong way here. Pi times the natural log of 2 times cosine of pi x times 2 to the sine of pi x. So that's problem number 31. If we look over at problem number 45, when we get to the problems with the words, and a lot of us get intimidated, like, oh, no, these are like word-oriented problems. No, they're really not. And they're the same words we've been encountering in every section of the book that we've done. When we look at problem 45, it says find the equation to the tangent line. Now we know what the equation to the tangent line is. We know the equation of the tangent line is y minus y1 equals m, which is going to be the derivative in our case, times x minus x1. And when we look at problem 45, they give us a function. They tell us y equals 2 divided by 1 plus e to the minus x. And our point is 0, 1. So right now, we know it's going to be y minus 1, y is 1, equals our slope. Now we're going to have to find that times x minus 0. Right? This is the big mystery. And to find that, we're going to have to take the derivative over. Now you could use the quotient rule. You could. But we now know the chain rule. I'm going to rewrite this as 2 times 1 plus e to the minus x to the minus 1. And now I'm going to take the derivative of that. Now, how do I take the derivative of that? I have a constant, so that stays. I have somebody to a power, right? That's how we say it. Somebody. We have an inside function to a power. So we have somebody to a power. What do you do with the power? You bring the power down. Perfect. What's your new power going to be? Well, you subtract 1. So that's going to be minus 2. But then remember, you have to take the derivative of what's inside. The derivative of 1, 0. The derivative of e to the minus x. Well, that's our friend the exponential again. And the derivative of the exponential is the exponential. So you just copy it down. But it's not x, it's minus x. So we have to use the chain rule. We have to multiply, because that's a function other than x. We have to multiply by the derivative of minus x. And that gives us minus 1. Now, if we simplify this, right, we have minus 1 and minus 1. That's positive. We have a 2 that goes on the top. This has a negative exponent. That has a negative exponent. So we have e to the x there. And we have 1 plus e to the minus x squared right there. Now, what are we going to do? We're going to plug in x is 0. When we plug in x is 0, right? So we're going to take y prime, we're going to evaluate it at x equals 0. We're going to get a 2 on the top because that's a constant. E to the 0 is 1. E to the 0 is 1, so this is 1 plus 1, that's 2 squared. So we get 2 divided by 4, or 1/2. So the The slope is 1/2. The equation of our tangent line then is y minus 1 equals 1/2 times x minus 0. So it's just like all the other equation of the tangent line problems we've seen before. We use the same vocabulary over and over and over again. So we don't have to be concerned about, oh no, there's some words. We've seen the words before. Okay, if we skip down to problem 49, right, we take a look down here at problem 49. What does problem 49 say? Again, it's got words, right? And they're the same words we've seen before. Find all the points on the graph of the function where the tangent line is horizontal. So this gives us f of x equals 2 sine x plus sine squared x. Now we know what it means when they say tangent line horizontal. That means the slope equals 0. That's what tangent line horizontal means. The slope equals 0. So I've got to find the derivative. I know how to do that. Now remember, sine squared means this, right? That's what it means. So we can use the chain rule here. F prime of x, the derivative of sine is cosine, so that's 2 cosine x, plus we have a power, that's our outside function. So the outside function, we take the derivative first. That means that power comes down. We get sine x, take away 1. We then take the derivative of what's inside and we get cosine x. Now, in factor, right, because we want to know, we want to set this equal to 0. So the only way we're going to be able to solve that is to factor. We have a common factor of 2, 2, 2. Common factor of cosine, we'll take that out. And here we're going to have a 1, and here we're going to have sine. Now we have a rule, right? We're going to set f prime of x equal to 0 because they said horizontal tangent lines. We have a rule that says if you multiply things together and get 0, right? It's called the zero product property from back in math. It said if a times b equals 0, then a equals 0 or b equals 0. One of the two factors must be 0. We know 2 is not 0, so that means cosine is going to equal 0, or 1 plus sine is going to equal 0. Now, how do we know when cosine equals 0? Well, if we draw the graph of cosine, cosine goes like this. And we know that's pi over 2. We know that's 3 pi over 2. We know that's 5 pi over 2. This is negative pi over 2, negative 3 pi over 2. And over here, we've got negative 5 pi over 2, right? That's how cosine works. So when does cosine equal 0? Well, it equals 0 when we have a pi over 2 and our coefficient 1, 3, 5, 7, 9. Our coefficient is odd. So that means we have a pi over 2. And we have to have an odd coefficient. The way in math we write odd numbers is we write 2k plus 1. 2 times a number is even. 2 times a number is even. That's why we put the coefficient of 2 here. 2 times a number is even. When I add 1, automatically going to be odd. Even numbers plus 1 turn out to be odd numbers. And then we say where k is an integer. And that's all the odd multiples of pi over 2. Now here, if we solve this, if this says sine x equals negative 1. If we draw the graph of sine, we have some room down here. So if we draw the graph of sine, sine goes like this. Sine is negative right here, right here, right here, and right here. This is negative pi over 2. This is 3 pi over 2. This is 7 pi over 2. This is negative 5 pi over 2. And if we take a look, we already have all of these numbers. Well, it would be this one right here, accounted for in our previous answer. So this is going to be where the tangent line is horizontal. So that's number 49. If we look at a problem like 51, right? We've done problems like 51 and 53. So 51 is just like 53, but 53 involves a table. So I'll do 53, and then you can go back and apply the ideas from 53 to problem 51. Okay. So 53 says part A, right? It gives us a function. It says h of x is a composition of f of g of x. That's what it says. It says find h prime of 1. Okay, find h prime of 1. So we want to take the derivative of h. Now we know what the derivative of h is going to be. H is literally this function right there. The derivative of that is going to be f prime evaluated at g by the chain rule, outside function evaluated at the inside, times the derivative of g. But they want us to find this at 1. And now they gave us a table, right? They gave us a table. In the table, they gave us values. First column is f, next column is g, then f prime. So they gave us a table, and the table looks like this. And I'll go ahead and write the table over here just so everybody's clear. We have x, and we have 1, 2, 3. And then we have f of x, and we have 3, 1, 7. Then we have g of x, and we have 2, 8, 2. Then we have f prime of x, and we have 4, 5, 7. And then finally we have g prime of x, and we have 6, 7, 9. So this is given to us in the book. Well, if we look at this, this is g of 1. G of 1, here's 1, g of 1 is 2. So this becomes f prime of 2, because g of 1 from our table, here's our x value of 1, g of 1 is 2. G prime of 1, here's g prime. G prime of 1 is 6. So this is going to be times 6. Well, now I need to know what f prime of 2 is. Well, f prime is this column right here. Here's 2. F prime of 2 is 5. So I get 5 times 6, or I get 30. Okay. So I'll leave part B for you to work on. 51 is exactly the same steps, but instead of having it in a table, they just give you a list of the values in the problem. All right. 55 works out exactly the same, but instead of giving it to you in a table, they give it to you on a graph. So you have to actually go, if x is 1, where am I on the curve? And you can find the y value. Now, if we take a look at 62, all right? If we take a look at 62, let's go ahead and erase this. 62 says g is a twice differentiable function. All right, that's what we know. We know we can take the derivative of g twice, and they give us f of x. It's x times some function g of x squared. We don't know what g is, but we know it has a derivative and it has a second derivative. That's what twice differentiable means. It has a derivative and it has a second derivative. So if I'm going to take the derivative of f, which is what they asked me to do, they want me to find f double prime. So to find that, I have to take the derivative of f. So I'm going to have to do the product rule. The derivative of x, 1. leave G alone. All right, that's how the product rule works. Plus, leave the first function alone. Take the derivative of G. Now we have a function on the outside and a function on the inside. The outside function is G, so we take its derivative first. So we get G prime, we leave X squared alone. All right, because that's what it says. Outside function, leave the inside function alone. Times the inside function. Sorry, times the inside function's derivative. And so we're left with this. So what do we have for F prime? We have G of X squared, right? G of X squared, plus, and if we multiply this out, we have 2x squared G prime of X squared. Now, I don't know what G of X squared is. I don't know what G prime of X squared is. That's my first derivative. How do I find my second derivative? I take the derivative of G of X squared. Well, we just took the derivative of G of X squared in our previous step, right there. That was the derivative of G of X squared. So we don't have to rethink our way through that. We can just copy that down. The derivative of G of X squared was 2x G prime of X squared, right? It's right there. There it is, right there. Plus, now we have to use product rule again. This is my F. Pardon my use of letters here, but this is my G from the product rule. Right? That G and that G, completely different G's, of course. So I take the derivative of the first term, 2x squared. The derivative of that is 4x. I leave this alone. Plus, I leave the 2x squared alone. I take the derivative of G prime of X squared. Well, I got a function with an inside function. The derivative of G prime, G double prime, leave the inside function alone. Now take the derivative of X squared. 2x. Now we ask ourselves, is there anything we can factor out of any of these functions? Right? Do we have any common factors? Here's a 2x. There's obviously a 2x in here. Here's a 2x over here. So we can pull out a 2x. That's it. That's all we can pull out. Here we're left with G prime of X squared. Now we took a 2x out, so that leaves us a 2. So we've got plus, right? We took a 2x out, so that leaves us a 2 G prime of X squared. Now those can be put together. And over here we took out a 2x, and we have plus 2x squared G prime, double prime, pardon me, of X squared. So these two things can be combined, right? There's one of them right there, plus two of them. So our final answer is going to be 3 of those. All right. Now, from here, there's problems 79, 80, and 82, and those are no different than problems we've done in the past. It says find the equation of the tangent line to the curve given the value of the parameter. Now, we don't know anything about parametric equations. We didn't cover that section in the book. So you can skip problems 79, 80, and you can skip problems 82 as well. So 79, 80, and 82, you do not have to do. All right, that completes our homework